A surgeon in London is about to operate, but the patient is in Dubai. The only thing standing between a successful procedure and a catastrophe is the network. Not Wi-Fi, not fiber, a 5G network doing something most people have never heard of. By the end of this video, you will understand exactly how that is possible and why it changes everything about how we think about connectivity. That scenario is not science fiction. It is a 5G network slicing use case already being trialed today. 4.9 milliseconds of latency. One physical network, two cities connected as if they were one room. The technology that makes this possible is called network slicing, and it is one of the most important, most misunderstood capabilities in 5G. Here is what we are going to cover today. Here is the roadmap for today's video. It is important that you stay with me till the end of this video so that you get the answer to the question that the telecommunication industry doesn't want to admit. We start with the problem, why one network cannot serve everyone equally. Then we use an analogy to make the concept click instantly. From there we go deep, the architecture, the three slice types, the use cases that are actually working today. Then, and this is the part most explainer videos skip, we get honest about the challenges, the real-world deployments, and where this technology is actually headed. And at the end, I'm going to answer the one question nobody in the telecom industry wants to give a straight answer to. If slicing is so powerful, why can't you use it from your phone right now? Let's go. Think about three completely different users of the same mobile network. A hospital running remote diagnostics, connected wearables, and AR-assisted surgery support. They need predictable, reliable latency because a delay is not an inconvenience, it is a clinical risk. A smart factory running robots, machine vision systems, and automated guided vehicles. They need deterministic performance. The network cannot have a bad moment when a robot arm is in motion. And a packed stadium, 80,000 people uploading videos, checking scores, and streaming at the same time. They need scale, sheer massive throughput. One network, three completely different requirements. Traditional mobile networks are built to serve averages across all three, and that compromise serves none of them well. That is the problem 5G network slicing was designed to solve. Legacy networks are like a highway where every vehicle, ambulance, freight truck, family car, and bicycle follows exactly the same rules and gets exactly the same road priority. That is fine when the goal is to move as many vehicles as possible, but it breaks down the moment you need an ambulance to get through in under 2 minutes. 5G slicing changes the model entirely. Instead of one set of rules for everyone, the network can create logically separate environments, each with its own performance guarantees, its own resource allocation, its own security posture. The key word is end-to-end. Slicing is not just a radio feature. It is not just a core feature. It has to span the entire network, radio access, transport, and core to actually work. That is what makes it powerful. And that is also what makes it hard to build. Let me give you a mental model that makes this click immediately. Imagine a highway. One road, but 4 lanes, each with completely different rules, reservations, and performance expectations. The emergency lane is reserved. Only authorized vehicles. Guaranteed clear passage. That is your URLLC slice, your hospital, your surgical robot, your safety system. The freight lane is for heavy, reliable loads, scheduled, predictable. That is your industrial IoT slice, factories, machine control, logistics. The express lane is for high-speed, high-volume traffic. That is your eMBB slice, streaming, cloud gaming, augmented reality. And the mass lane, millions of slow-moving, low-priority vehicles. That is your IoT slice, sensors, meters, trackers. The road is the same, the asphalt is the same, but the behavior, the guarantees, the rules are completely different in each lane. That is exactly what network slicing does. Now here is where the highway analogy becomes even more powerful, and also where it falls short. Painted lane markings are fixed. You cannot add a new emergency lane at 7 p.m. because there is a match tonight and remove it at midnight. You cannot dynamically widen the freight lane on a Tuesday because a factory is running at full production. Network slices can do exactly that. Because slices are software defined, they are created in software, managed by orchestration systems, and can be modified or removed without touching a single piece of physical infrastructure. Think about what that means for a broadcaster. They need a guaranteed high-priority connection for a live match. They request a slice at 7 p.m. They get it. Halftime they need more uplink capacity. The system adjusts automatically. Match over at 10:30 p.m. the slice is terminated. The resources go back into the shared pool. That is not a fixed lane, that is programmable infrastructure, and that changes the entire business model of networking. 3GPP standards in telecommunications define slicing as dedicated logical networks with specific characteristics on shared infrastructure. Strip out the standards language and you get three pillars. Performance. The slice is tuned to the service. Isolation. One slice's bad day doesn't affect another's. Orchestration. The whole thing is software managed and lifecycle driven. The network slicing architecture has three layers. At the top, the service layer defines business intent, what the slice must deliver and for whom. In the middle, the management layer translates that intent into templates, policy, orchestration, and lifecycle control. At the bottom, the resource layer is where the actual infrastructure lives: radio, transport, core, edge, and cloud. The important point is this: any one layer on its own is not network slicing. Slicing only becomes real when business intent is connected all the way down to infrastructure behavior. This is the most important technical point in this video. Slicing is not a radio feature. It is not just a core feature. It is an end-to-end service architecture. If your RAN supports slicing, but your transport does not, you do not have slicing. If your core is slice-aware, but the operational model cannot enforce the SLA across the rest of the path, you still do not have slicing. What makes slicing commercially meaningful is coordinated behavior across every network domain that touches the service. The industry usually talks about three reference service families for network slicing. eMBB is enhanced mobile broadband that provides high throughput, dense user scenarios, streaming, XR, and premium consumer experience. URLLC is ultra-reliable low-latency communication, which is the hardest category, built for industrial control, safety systems, and robotics. And mMTC is massive machine-type communication focusing on huge device density, low power, low data rate, and very different economics. These are useful mental models, but they are not fixed commercial boxes. They are reference patterns for what the network is trying to optimize. This is where the textbook view starts to break down. Real deployments do not choose one slice family and stop there. A smart factory might run a URLLC-oriented slice for robot control and safety systems, while also running an mMTC-oriented slice for sensor telemetry, maintenance data, and wide area asset monitoring. Same physical 5G infrastructure, different traffic classes, different service expectations. That is much closer to commercial reality than the neat three-box diagrams people usually show. Let us make this concrete with a factory. In the control zone, you have robots, programmable logic controllers, and safety-related motion systems. That environment needs very high reliability and very predictable network behavior. In the vision zone, you have high-definition cameras and AI inspection workflows pushing heavy uplink traffic into edge compute. And in the logistics zone, you have AGVs, warehouse visibility, and sensor coverage spread across the site. Those are three very different connectivity problems. Slicing is what lets one 5G network support all three without building three separate infrastructures. Beyond factories, slicing makes sense anywhere the workload is heterogeneous. In healthcare, you may want patient-critical traffic isolated from general hospital connectivity. In utilities, telemetry and control traffic should not behave like employee broadband. In airports, baggage systems, airline operations, retail services, and passenger connectivity all create different demands on the same infrastructure. In live events, you may need one profile for production, another for venue operations, and another for the crowd. The broader the workload mix, the stronger the logic for slicing becomes. This is the comparison most people get wrong. How is network slicing different from private 5G? A network slice is a logical service delivered on the operator's shared infrastructure. Private 5G, on the other hand, is a dedicated network, usually built for one enterprise, one campus, or one operational environment. That changes the ownership model, the isolation depth, the coverage pattern, and the cost structure. But the real nuance is this: they are not always competitors. In some enterprise strategies, slicing extends wide area services, while private 5G handles the most tightly controlled on-site environment. The right answer depends on the workload, the control requirement, and the commercial model. Slicing is not a one-time configuration. It is a life cycle. Design sets the intent and template. Instantiate allocates and configures. Activate takes it live. Modify is where real operational intelligence kicks in, demand changes, SLAs drift, the system responds. Terminate reclaims resources cleanly. Without automation across this entire loop, slicing does not scale commercially. This is why cloud-native core maturity was the missing piece for years. I have spent the last 10 minutes telling you how powerful network slicing is. So here is the question you are probably asking. If slicing is real and it works, why cannot I open my phone settings right now and pick a low latency slice the way I pick a Wi-Fi network? The answer might surprise you, and it tells you more about the business of telecom than any technical spec ever will. Keep watching. 4 things are slowing commercial adoption. First, orchestration that genuinely spans RAN, transport, and core is still maturing in most operator environments. Second, assurance where you cannot promise differentiated SLAs unless you can measure and enforce them in near real time. Third, devices. Most handsets do not expose slice selection to the user cleanly. Fourth, commercial packaging. Enterprises buy outcomes, not acronyms. Here is the answer I promised you. Consumer slice selection from a phone menu does not exist at scale yet because the economics do not support it. The most valuable slice use cases are enterprise contracts like a hospital SLA, a factory automation package, a broadcast event guarantee. That is where operators make real money on slicing. You, the consumer, benefit indirectly through better network design, but you do not get a menu. Not yet. Network slicing is not a white paper promise. SK Telecom, Deutsche Telekom, Singtel, Telstra, Verizon, and vendor-operator partnerships like TIM have all moved slicing into trials or early commercial deployment. Study what kind of slicing each one emphasizes: enterprise SLAs, campus networks, API exposure, and you will understand where the business model is actually landing. Let me give you the numbers you will hear everywhere for network slicing with honest context. Sub 1 millisecond is an aspiration for the most demanding URLLC use cases, not everyday consumer reality. 20 gigabits per second is a peak rate headline, not average user experience. 1 million devices per square kilometer is the mMTC design target. The $11.2 billion market signal tells you where investor attention is. 6 nines of reliability is a shorthand for critical service availability. Release 15 is the 5G baseline that opened this entire conversation. Let's talk about the roadmap of network slicing. In the near term, more targeted enterprise offers where 5G SA and automation have matured. 2026 to 2027. Better API exposure, assurance tooling, and edge integrated packages. The medium term brings stronger ecosystem support across devices and cloud-native operations. In the long term, intent-driven, AI-assisted networks with autonomous slice adaptation. That is also the bridge to 6G programmable, self-managing networks, where slicing is the baseline, not the premium feature. Let us crystallize this. 1. Slicing is logical partitioning with differentiated service behavior on shared physical infrastructure. 2. It only works end-to-end. Isolated tweaks in one domain are not slicing. 3. eMBB, URLLC, and mMTC are useful guides, but commercial reality is more customized. 4. Enterprise use cases are the clearest monetization path today. 5. The barriers are as much operational and commercial as technical. Here is the thought I want to leave you with. Network slicing is not just a telecom product. It is the first concrete step toward networks that are software-defined end-to-end, where connectivity is not a commodity pipe, but a programmable service. That idea does not stop at 5G. It is the foundation of every 6G vision paper being written right now. And Techtonic is going to cover all of it. If this video gave you a clearer picture of slicing than anything you have read before, hit subscribe. Tune into Techtonic for deep dive on interesting topics on advanced networks every week. Drop a comment with the use case you want unpacked next. And if you work in enterprise wireless, share this. Most of your colleagues have heard the term and do not actually know what it means.